recording session. Recording on? All right. Okay. All right. So let's start with the first session in the whole series. The topic here is cap theorem. If I don't know whether you tried reading about cap theorem in the past. Every time I read it, it kind of makes sense when I'm reading it. But if after a few months, if I have to explain this to someone or if I have to think about it, I will get confused. Yes, because probably it was written in a slightly non-intuitive manner, not by the original author of this, but many blogs and articles wherever we see it. They usually talk about the three factors: C for consistency, A for availability, P for partition, network partition, and then there are some Venn diagrams and that kind of explanation. I try to put them in a kind of intuitive manner. Let's see how this works for all of us here. Now, I want to cover this in four topics here. Number one is what we call linearizability. The original term is consistency, but linearizability is a little more academic and far more refined than consistency. So let's explain what linearizability is and understand what it takes to build systems, use what we call the linearizable systems. And along the way, the implications will come out very apparent, and that's what cap theorem is all about. So this is the approach that I want to take to get to the cap theorem by understanding what this is, some use cases, some of the implementation techniques, the implications of it, eventually leading us to this. So let's get started first with understanding the linearizability itself. Now, I've taken a fun example here. So this is the World Cup FIFA 2018. And imagine that there are these two people, Alice and Bob, who are sitting in a restaurant or a pub somewhere. Each of them are holding a phone and they are refreshing their phones, trying to find out the result of the World Cup that's going on. Apparently, they're in a place where there is no TV. Let's imagine that. So they have to use their phones. Now, the system behind is massively distributed because the millions of people, hundreds of millions of people are following this. And therefore, there is a leader system into which the referees, who are the final decision makers, are updating the status of the match. So there is a final scores table where they are putting in France, the latest scores is France is 4 and Croatia 2. And when something is updated like this, that's the end of the match. And obviously France had won the match. So that insert goes into a leader database and it got successfully inserted. Everything is fine. Now, there are many other following systems, what we call the follower 1 and follower 2, where this update will have to be propagated in an asynchronous manner. So let's say follower 1 got a notification to update itself, and it has finished its work. And follower 2 also gets an update notification along the timeline, slightly delayed, and it is also performing its own update. So while this is happening, Alice, her phone is now connected to follower 1 by some means of routing. So when Alice is refreshing the phone, because the update has already happened, so the system will say, France has won it. So Alice is now shouting in joy, France has won the World Cup. Upon hearing this, Bob is also refreshing his own phone. He couldn't believe what she says. So he's refreshing his phone, which is connected to follower 2. So what happens here is that the update is still pending, and Bob doesn't see anything in the final scores, and therefore, according to him, the game is not over yet. So now Bob is surprised, and Alice also is surprised. What's happening here? So what has happened here is Bob now is kind of back in time. So he's not in real time according to this entire system. So here is a linearizability problem. And this is one way to understand. And this timeline's way of describing multiple systems and the user accesses, this is very innovative, and I kind of like it. It's very intuitive to to discuss such things. So we can probably use this swim lane model in our own analysis also. So if you look at linearizability definition, basically what it says is that the basic idea is simple. The system has to appear as if there is only one single copy of data. That's very straightforward and the simplest definition. And this is how the world was in the past, when we used to deal with monolithic systems where there is only one single database and using ACID properties. By the way, the C in the ACID is consistency, and by default it is there in an ACID compliant database. The world was very simple, and everything is, of course, linearizable. When you put an update, once the update is successful, any read will, any number of reads in any point in time in the future will always see a consistent result. It will never be the case as we saw before. But that was the world where there's only a single database and everything worked fine. Now, let's get into a little more of formal definition of this, one level deeper. So here, if you look at, there are 3 clients who are all working independently of each other, but they are trying to update a same variable. Now I'm formalizing the whole thing we discussed. Let's say X is the register, and there are 2 operations supported. Either you read the value from the register, or you update the register by using a write operation. You specify the register name and the value, and it is supposed to update the register. Now, these guys can read and write at their own will at any point in time. And the box represents, the left side of the box is when the client initiated the transaction of reading or writing. The right-hand side is when it finishes, which means between any time from the left to right, the database will be, or the register will be updating. We don't know when it will update. So this kind of a scenario, when the client A is reading, he's getting the value 0. The only parallel activity is client C is writing into the register. Now, as the write operation is happening, there are 3 reads that are overlapping when the write operation is happening. And depending on when the write operation finishes in the database, the reads will either return 0 or 1. Yeah, this is how it used to be, right? Because we never know when the write is getting updated into the database. But once the write is over, consistently the reads will be returning the most updated recent value, which is 1. So this is the simplest behavior. Now, the linearizability academic definition of this is that suppose if one of the client is able to read the updated value, so which basically means that somewhere before here, the write has finished in the database. So the first client has read 1. Right after that, any other client who is reading it should be able to see the same 1, even though the write operation itself is still going on. It's not finished yet. But nevertheless, once one client has seen 1, the rest of the clients must consistently see 1. And that is what we call a strictly linearizable system, or the definitions of atomic consistency, strong consistency, immediate consistency is all about this. So if you relate this back to the scenario of the World Cup, Bob and Alice, once Alice had seen the latest value, subsequent read from Bob should match with that. Although that replica that Bob is connecting to is still being updated, but once the first read has written the latest result, subsequent reads must return the same. So that's the pure definition of linearizability or strong consistency. So far, okay?
Just one thing, Dada.
Yeah.
In the previous one, you were talking about the insert is happening from a place. If you can go back to that. Okay. So insert is happening into 2 different places or 2 different databases from where the 2 people are reading. But with this one, you're talking about the writing would be happening at one place, right? Or it'll be happening at...
It's still the same. It doesn't matter. Basically, this is the conceptual perspective from a client side. Internally, it could be one database or multiple databases. So again, if you look at the definition of linearizability, it has to appear as though there is a single copy to the client. Behind the scenes, it could be one or multiple. It should not matter for the client. Yeah, that's the idea here.
Okay.
And this one takes it to a little bit deeper to say that one client has read the latest. Any read after that must be the latest also, even though the update is still in progress. So this is trying to make it very tighter and extremely consistent, or this kind of strong consistency explanations. So this is all very academic at the moment, but it's important that we understand the stronger consistency and the meaning of it. Now, where are we really requiring these kind of consistencies? So if you look at use cases, most of us would have encountered these use cases in the past. So we talk about linearizability is a recency guarantee on reads and writes of an individual object. So from a client perspective, we are able to always get the most recent updated value, whether we are reading or before writing. So that's the guarantee that linearizability is giving. So some small examples are, let's say, a system where we are creating user IDs. So imagine that I am reserving a user ID, and somebody with a similar name is also trying to reserve the same user ID. With linearizability, it is possible for the system to stop these two users from creating the same user ID. So back in your mind, you imagine if it is a distributed database with multiple replicas, users connecting to different replicas, you will understand the challenge of implementing linearizability in that case. Yeah. Similarly, a banking transaction, obviously account balance should never go negative. The transaction should stop before that if the customer is withdrawing money or making payments. Again, the linearizability is important to maintain this level of consistency. Retail scenarios, don't sell more items than in the warehouse stock, or booking for flights or theaters, two users booking the same seat. So these are scenarios where linearizability is extremely important to implement. Otherwise, it leads to complete chaos. And some of the non-business use cases, for example, what happens within a zookeeper, where when the leader election happens, there is some distributed locking that happens. Whoever gets the lock first will be elected as the leader. And that means there has to be a common consensus among all the nodes about who has actually won the lock. Linearizability is the most important factor in these kind of scenarios. The Oracle's original clustering, which is called replication cluster, RAC, where there are multiple nodes where there is a contention to lock a single page in the database underneath. So there again, there has to be linearizability comes in to say that who actually got the lock and who got the right to update given a particular point in time. So these are examples where in the past it's very natural for us to think of a relational database, a single database using ACID. We will be able to achieve it. Now the challenge is if we think about implementing them in a distributed system. So that's where we need to expand our thinking and see what is possible. How much it's possible to enforce linearizability. Now, let's go to the next topic is implementing linearizability itself. So I'm going to put some thinking using the distributed systems as a context. So once again, reiterating, we are saying that the database system have to behave as if there is only one copy of data and all operations are atomic. This is the perspective that a distributed system should give to the client, although behind it could be one or more or n number of databases partitioned, replicated behind that. So obviously, it's easy to do it with a single database, but single database won't scale, won't tolerate faults. and this is the fundamental reason why we started distributed computing in the first place. Now, if you look at the most common approach for fault tolerance, which is replication, right? So in Bob Ellis' example also, we saw that there is a leader, there are multiple replicas, and that's what is providing the capability for failover as well as scalability. And there are 4 techniques involved in data replication. We have a special topic on replication where I think Rajiv or someone is going to present these things in detail. But I will just touch upon them only from a linearizability perspective. So we have single leader replication, multi-leader, leaderless, and there are some consensus algorithms, which is slightly older technique. So in these 4 different schemes, which of them is helping us to implement linearizability and which won't? So let's look at that to start with. So here is a summary of everything. What in a single leader replication, essentially what happens is all writes will be sent to a single leader, like what is happening in Kafka at the moment. You are writing to a leader, and the leader will be synchronously, not in case of Kafka, but generally synchronously replicating to the followers. Only then a write operation is finishing. So in such scenario, we can potentially implement linearizability. I say potential, later I'll explain why it is not completely guaranteeing linearizability. So imagine that there is a leader where all the writes are going to, and the leader synchronously replicates before it says OK. That means subsequent reads, whether you are going to the leader or you are going to the replica, we are always seeing the latest consistent data. So that's pretty good here. Now, if you look at multi-leader replication strategies, again, this is needed for certain use cases. It's extremely useful. But when it comes to linearizability implementations, this is not going to give us linearizability no matter what. The reason is because in a multi-leader replication, there's no single leader. That means writes can go to multiple leaders, and each of them will eventually communicate to the rest of the follow. And therefore, this system, given some time, will eventually converge into a single source of truth, but eventually. And it also has to resolve a lot of write conflicts. It has to see which write happened before and later, and it has to resolve that. And then finally, a consistent state will emerge. But in the meantime, there is no version of single copy. Therefore, it is not suitable for implementing linearizable use cases. It's very, very clear in case of multi-leader replication. So far, so good.
Yeah.
Okay. Now, there is this method of leaderless replication, which is basically quorum-based consensus derivation. So I'm sure we will see this in detail in the replication topic. But at a very high level, if there are nodes in the system, and let's imagine that we are able to write into W number of nodes, and we are able to read from R number of nodes. If this sum of these nodes is greater than the total number of nodes in the cluster, pretty much you know that the system is operational. So for example, if you have, let's say, 3 nodes in the cluster, I'm able to write into 2 nodes. The third node I'm not able to reach, let's say. And I'm able to read from 2 of these nodes. So this sum will become 4, and which is greater than 3. Therefore, the complete cluster will continue to operate. But there are scenarios where this equation doesn't work. Imagine if there are 4 nodes, and you are able to read from write to 3 nodes, and if you are able to read from only 2 nodes, and suppose the second node is the one that you could not write to, let us say. Although the quorum rule is passing, you will not be able to make a conclusion on whether your data that you are reading is agreeable or not. So anyway, we'll see the details in that topic, but even what it says is that there are scenarios where this will break also, and therefore leader's replication cannot give us a linearizable system. Okay. Now the last one is consensus algorithm. So this is where the very old distributed commits, the 2-phase commits and 3-phase commits all comes in. Essentially, it is similar to the leader replication, but instead of a leader, this is going to be an external coordinator, what we call the transaction manager, who is coordinating these transactions, and he checks with every party involved, and if everybody is confirmed, then he would say that the transaction is committed, and that's why this is suitable for linearizable systems, but the cost is very high. Obviously, linearization comes with a lot of cost also. So that's the very big overview of the replication techniques and what supports linearizability, what does not support linearizability. You can straight away minus off these two and then only look at these two guys when it comes to implementing linearizability. Now, although we say it's possible, right? Now, this is where CAP theorem comes in to state the limitations. Okay. So let's look at the limitation here. This is a lot of words, but let me explain. If the application requires linearizability, so for example, in terms of a bank scenario, linearizability is a must, let us say. And in this case, if it's a distributed system, and some replicas are disconnected from other replicas, there is a network breakdown in between. The replicas are alive, but they are disconnected, which means what? The updates cannot go to those disconnected replicas. Yeah. But linearizability is important in this case. So in this scenario, the replicas cannot process the request. We should not allow these replicas to process the request, because if you allow them to process, they will have stale data. Yeah. Therefore, the whole system must either wait until the problem is fixed or should return an error. Basically, it should not allow transactions to happen. So that means essentially what we are saying is that the system becomes unavailable because it needs strong linearizability. The system has to go unavailable. There is no other way of providing this high consistency in this scenario. So let me explain with an example here. So let's say we have 3 replicas. Now user is doing an update. So he is setting the picture of a particular user. He's uploading a new picture for the user. So let's say this is a single leader synchronized replication. So replica 1 is updated. Replica 2 is also successfully updated. While updating replica 3, there is a network problem between this. So the replica 3 is not reachable, but it is still alive. Therefore, replica 3 could not get the latest update. So the implication is, if you are reading, if I'm reading from replica 1, I'm going to get the new picture. If I read into replica 2, I'll get the new picture. Anyone reading replica 3 is going to get the old picture only, not the new picture. And here we have violated the linearizability, right? So because the system demands this linearizability, we should, if this is the scenario, the whole system should stop accepting any transactions. Only that way the data between these replicas remains consistent, and that means we are becoming unavailable. So it impacts the availability of this system. So far, so good?
Yes.
Okay.
Yes, sir.
Now, what about this scenario? If your application does not require linearizability, so let's say linearizability is not a big constraint. Bob and Alice, eventually Bob may refresh many times, and eventually he will come to know, not a big deal. So that means we do not require linearizability. In that case, what we can do is, although replicas are going out of the network, you can still, the application can remain available and can accept the transactions. But what we have sacrificed is that the linearizability. So if you want to make the application available continuously, then the consistency is lost. We can't have it. Okay. So that's the flip side of the first rule that we saw. So if you have to put everything into picture, cap theorem, we can forget about all the Venn diagrams, the what is there and what is not, and the jargons are completely not very intuitive. So all we have to see is in a partitioned system like this, when there is a problem with the network connectivity like this, then you have to choose either linearizability or availability. You can have only one of it. You cannot have both. That is basically the limitation that cap theorem is talking about. It's very, very straightforward in this case. Okay. So, but when the network is working correctly, everything is going fine, obviously we are getting linearizability and very high availability. But when the network is not, is broken in between, when the system's nodes cannot see each other, then the system has to be designed either to have high availability or to have high consistency. It cannot have both. So if you want to take some, let's take some practical examples here. So let's say we are using, we are designing a Redis system. There is a master and a slave. Master is in this case, master is the leader, right? So all writes goes through the master, and there are slaves that are getting written, that gets replicated data. But the slaves are reading slaves, so people can read from these slaves. Suppose if you are using a banking system implemented in this manner, if one of the slave is not reachable, obviously some customer who is connected to that slave and reading data is not going to see the correct account balance, which is extremely a dangerous scenario. And therefore, a banking system has to honor the high consistency. And in such scenario, the banking system should return an error and stop accepting transactions. But let's say there is a system that is giving the tennis scores. Obviously, it is not highly critical. People may be connecting to the slave, which is not giving the latest scores. But when the network comes back with the proper algorithms behind where the slave can read and update itself, eventually things will become all right. So it's not a big deal. So in such use cases, the availability is given a higher priority. Consistency is not that important, and therefore we can work in that way. So understanding this, limitation helps to design systems with some architectural principles way up front. And also, this has led to this eventually consistent NoSQL databases. After the cap theorem is formalized, this is when the explosion of eventually consistent database, NoSQL databases started to come about. And because the use cases can be designed with this in mind. Now, some criticism about cap theorem is that it only talks about network errors. But there can be many things that can go wrong in a distributed systems. What about network is okay, but there are delays. So what do we do with that? Nodes die, but nodes come back. A leader dies, another leader is selected, but the original leader comes back thinking he is the leader. Now you have a system with the split brain personality. There are two leaders. So how to handle that? And there are many things in a distributed system that can go wrong, and we need to answer that. But cap theorem just talks about only one such failure, and that's where it stands. So we should not be thinking that this explains everything about in a distributed system. Okay. So that's the last one. Long talk about something very simple and intuitive. How do you feel? Is it clear?
It's clear. One example I was just thinking while you were you're comparing the availability and the linearizability. So the Twitter, what they do, I was reading about this one day. So whenever someone is posting a tweet or tweeting, so that tweet has to reach the various followers in the timeline. Okay. So what happens? Let's say if there is a person, let's say Narendra Modi, he's got millions of followers, and for that tweet to reach everyone, Twitter actually takes around 4 minutes. So that's the delay that you were talking about, network delay. So I think the way Twitter works, I think they are not taking care of the linearizability.
Linearizability as
They
a
are
great
taking care of the
yes,
availability.
absolutely. Because whenever I visit Twitter, I need to see something. It cannot be like there is nothing to show. So therefore, the availability is given a higher priority than the consistency, and that's exactly the CAP theorem's uh, limitation also. Which, yeah, that's a perfect example, sir.
Raja,
Yeah.
what should be our mode of thinking if, let's say, we are designing a system where some operations are require strong linearity and some don't? Let's say, for example, the banking system we discussed about. So updating a profile picture may not be. I mean, let's say I don't want linearizability into this. If it is available after 2 days, it's okay. But when I'm doing a money transfer or banking specific transaction, then it should be highly linearizable.
Absolutely, absolutely. So I mean, if a system needs 100% linearizability, you would be implementing in one of these methods. Either you would be following the second method, which is you will be using two-phase commits for those things. But if you have a hybrid system where some transactions have to be highly linearizable and some are not, then you definitely have to have a mixture of both. So you may have a transaction which uses commits, two-phase, three-phase commits, whatever commits it is, and the rest of the transactions can go through a lazy replication through a Kafka exchange in between. So now the system has to recognize which path each of these transactions should go through. Okay. Any other questions so far?
No.
Okay. So if it's good, Suresh, we can stop recording on this. Then we can start the next topic.
Okay, before ending it, I just want to highlight only one thing here. So, though we have the consistency, availability, and partition tolerance, when we are talking about distributed systems, what we cannot tolerate is that partition tolerance is a must, right? Like we are not talking about monolithic systems. We are talking about distributed systems. So partition tolerance is a must. So the only choice what we need to make on the distributed system is either you want a consistency or availability. So even on the banking system, as we are talking about, what happens is like when a particular request is coming, and if the system is not able to reach, it's always a choice. Right? Like when either I want to show him, say that at the current moment, this is your balance. If he's able to connect, if he's not able to connect, I could still serve them the request saying that this is the last updated as of this time. But there, we won't say it is available, but still there's a bit of consistency here, meaning I am able to render him the pages, but I am saying that you cannot do certain transaction because I am not able to get the up-to-date information, so I am not able to complete the transaction. Right, when you're designing consideration, while doing design for the distributed systems, these we cannot strictly go by saying that availability, meaning like it is there, or we just show 404 or 503 error. It's not that way, right? Like it's something more to that, right? Only one functionality of it. Say my transaction is not able to go through, or I'm not able to get the updated balance because I'm not able to connect to the master node. Then I would have a choice saying that my system is not available now. You can't do a transaction now, but you can still view your existing transaction, old transactions you can see.
Right. Yeah. That's gracefully handling the scenario.
Handling, you just why I highlight just on to the point of consideration. I am saying how do we gracefully handle the scenarios.
Yeah. So you can say that this particular transaction that needs high linearizability that is not available at this point in time, but obviously the other portions depends whatever it is, it may be available. So that's a graceful handling at the client side. But nevertheless, the constraint is like you say, network partition is a given in a distributed system. Obviously, the data is going to be replicated. So that's a given. Now, when the network is healthy, everything is good, there is no problem at all. But when the connectivity is a problem, that's when the consideration itself comes in, whether we want to honor the high availability or we want to honor linearizability, and we have to make a decision on one or the other. It cannot be both. Yeah,
Right.
that's a good summary of what CAP theorem
But
says.
we are not talking about this P, isn't it, Raja? Because either C or A, we are only talking about the consistency or availability. Say there could be cases where my availability is important. I may not consider partition tolerance. So consistency and availability. Also, I can have it. If it is a monolithic application, not every application requires partition tolerance. In that case, I can still say that partition tolerance is not important for me. I need consistency and availability. So I can have these two, right?
Then we are talking about the old monolithic single database kind of.
No, Raja. When we are saying CAP theorem, consistency, atomicity can coexist together,
Consistent
and availability.
can coexist together when the network
Partition
is fine.
not my concern.
No,
Partition tolerance is if I am not not concerned much about partition tolerance, then I can still have a consistency availability together.
no, see, when you say partition tolerance is not your concern, the only possibility of this architecture is it's a single monolithic database. That's all you have.
Yeah, Raja. But to put it in a bigger picture, to understand that CAP theorem as a looking at a whole.
There is no need of a CAP theorem if you are a single monolithic database because it is already consistent with the acid nature. They were already consistent, but they were not high available, right? Because if that single database goes down, the whole system is not available. Therefore, such systems are not available.
No, I don't get this point because the CAP theorem is nothing to do with the distributed systems. Why we are talking about CAP theorem is that we have these three consistency, availability, partition, tolerance. Either only two you could have at any point in time. All three we can't have it. That's the basic idea, isn't it, Raja? If I'm not wrong, in the CAP theorem, what it says is like only two of it you can have, either C or P or A or P, other way around. So it is either two you could have it, not all three. So how you want to design it, that's left to us. But to understand, this is my understanding. If CAP theorem, if you say that we can't have all three together, only two, any two we can have at any point in time.
Yeah. It is. Yeah, if you look at general architecture, that makes sense. But in a distributed architecture, there is already network partition is a given. You have to have a data partition across. So that is a given. Yeah. You cannot call it a distributed system when you don't have data replicated across multiple systems. So that's a given actually.
Okay.
So when this is a given, then you only have you can only ensure availability or you can only ensure high availability, but not both. So this is purely a distributed systems perspective.
Yeah.
And the CAP theorem came in only for distributed systems. It was not there before. When the distributed theory starts, that's when CAP theorem itself is coming in to explain.
Okay.
Okay.
So Raja, what we can say about SIFT? Is it a highly linearizable system or highly available?
SIFT, if you look at okay, so this is looking at database only. So let's say we are talking about either Couchbase or Redis based implementation. We have multiple nodes in our database, and therefore we support high availability for sure. But if a node goes down and because of the eventual consistency nature of couch space, if a particular node goes down, suppose some replications from that node probably has not reached the copy, and therefore at that point in time our data is not consistent. So you can say that SIFT goes more towards high availability and less towards linearizability. But how serious is the problem? So if we have sized our database in such a way that replications don't take too long, in that case, the gap in eventual consistency is too narrow that the damage is very less, and that's what we are going towards.
But Raja, one more thing I want to add. With the internal cache that we have for our some of the operators, we are kind of in the middle of both, because the consistency is also there because we maintain a cache for most of the subscribers. But we are not entirely dependent on the couch space for that.
But we don't guarantee 100% linearizability. That's what you can say. But we do guarantee 100% availability, but not 100% linearizability.
Yeah. Eventual
consistency is what we are looking at.
This CAP theorem is only talking about when the application is working with the database, right?
Yeah, these are for data intensive applications. You're right. This is purely for data.
Because we cannot take core and try to implement this CAP theorem, right? It has to be whole SIFT, which involves database.
Correct. This is purely for data. It's not for compute related topics. Okay. So the simplest way is just take it from distributed systems only. Let's not look at anything before that. One of the factors called the network tolerance or network partition is a given in a distributed system. Let's start from there as the foundation. So given that this is the case, when the network is good, we can have both availability and linearizability. When the nodes can't see each other because of a network breakdown, then we can only have availability or linearizability. So if you remember it this way, we will never get confused in a distributed system world. Yeah, very straightforward. Okay, so let's end the topic here. Suresh, now we can stop. Okay.
I'll stop.